Hello everyone, I welcome you all to my YouTube channel. In the previous lecture we have discussed about the overview of stray current and the basic model of it. In this lecture we will be discussing about the most important parameters for the amount of stray current entering into our system, and also we will be looking into the criteria that are responsible for track protection and the development of stray current collection system. This was the basic model which we discussed in the previous lecture. Here Vs is your traction substation, your source. L here is your rolling stock, your load. Rc is the conductor resistance, that is the catenary or the third rail. Rr here is the resistance of the running rails. And Rs and Rl are your leakage resistance. So when there is a current flowing IL, that is the load current, it has to go back to its source. So it has two paths. First one is the longitudinal running rails. So most of the current flows through it, which is written here by IR, and there is some current leaking from the running rails and going back to the substation, which is IS, that is our stray current. As there is a current flowing in these running rails and there is a resistance, so as per Ohm's law there will be some voltage getting developed. This voltage is known as URE, which is the rail potential, and due to voltage across these 2 points there will be some stray current flowing through it, and this stray current can be written as URE times the track to earth conductance, that is GRE, or you can also write it as rail potential over the insulation resistance, as rail potential is the driving force for this stray current here. So these two equations are most important. Now as per section 5.1 of EN 50-122-2, which is the main standard, this standard is the main standard for stray currents in DC traction system. So this gives 4 important parameters. First one is GRE, that is the track to earth conductance. Here you can easily see from this equation that stray current is directly related to the track to earth conductance. Similarly, the other one is the distance between the substations. If you increase this distance, if the distance between the 2 substations increases, then the length of the running rail, the return path will increase. Due to more the length, more will be your running rail resistance. More the running rail resistance, more the rail potential. More the rail potential, that means more the stray current. Similarly, RR, the longitudinal resistance of the running rail, if it is increased, if you are not taking proper running rails, not up to the standard, or you are not doing proper welding between the 2 running rails, or you are not properly maintaining them, in that case this running rail resistance will increase due to some cracks and all. So if this value increases, then there will be an increase in the rail potential, and once the rail potential increases, your stray current increases. In order to reduce this running rail resistance, we do cross bonds. So if you are doing cross bonding, then this is your rail to rail bond between 2 rails, and this is your track bond between the upline and the downline. So if the spacing between these track bonds is higher, that means there will be more rail potential because your resistance will increase. If you do lesser spacing, if you have made the cross bonds at 250 meters or 300 meters, these track to track bonds, in this case your running rail resistance will increase due to more of paralleling. More the paralleling, lesser the resistance, and lesser will be your rail potential, so lesser your stray current. So these are the most important parameters. There are other parameters, but these are the most important given by the standard. Now going back to the criteria for the design of stray current collection system and for the track protection, as per clause 5.2 of EN 50-122-2, this is given in clause 5.2. So this clause states that track to earth conductance is the most influencing factor for the amount of stray current entering. Now the value of the stray current, which shall be limited in order to have a design life for 25 years for no damage for the track slab, in that case this stray current shall be lesser than 2.5 amps per kilometer or 2.5 milliamps per meter. Now this value is for only single track. For double track you have to multiply by 2. That means if upline and downline are there, then this value shall come 5 amps per kilometer. Now in some cases you might have to design for 50 years of design life. For that the standard does not specify, but you can assume a linear variation as there is no particular standard stating to take an exponential variation or a linear variation. So in case of 50 years of design life, you can reduce this value to half, and for 50 years this will become 1.25 amps per kilometer. That shall be the maximum value of the stray current when you are designing. Now, this clause also states the value of GRE, because which is the most influential factor. So this shall be less than 0.5 Siemens per kilometer. This is for open formation, and for closed formation this value is less than 2.5 Siemens per kilometer. Now open formation is where the running rails are kept on viaduct, they are open and they are exposed. For closed formation is it generally in the in the tram system, where it is embedded inside. The running rails are embedded inside an insulation cushion. So generally what we do, we design for this value. Normally the designers go with this value itself, that is 0.5 Siemens per kilometer. However, one of the most important parameter for governing this is also the rail potential. So this value is only valid in case your rail potential is also less than plus 5 volts, and in case of closed formation it shall be less than plus 1 volt. Now this value is an average value, and it shall be taken for the positive values of the rail potential and for a period of 24 hours. So this is generally given by the traction power simulation. However, this value can be increased. This value is generally increased if you have a headway of 90 seconds or 120 seconds. That means more number of trains will be running. So more number of trains will be running in one section. That means this IR will increase. If IR will increase, your rail potential will increase, thereby increasing your stray current. So this has to be taken in mind, that this is only valid in case your URE is less than plus 5 volts. Also, this value can increase for the rail potential if two substations are apart. Generally, in some of the metros, some two traction substations are 2 kilometers apart, but it happens that in case there is no provision to build a traction substation, then we provide at a distance of 3.5 or 4 kilometers. So as you increase the distance, your URE will increase. Once your URE increases, your IS has to increase. So you will not be able to obey this standard for the stray current value. So in order to avoid that, we generally go with a safety factor. We take this value as less 10 times, we divide this value by 10, so this comes out to be 0.05 Siemens per kilometer. And this 10 times is also done because this value is design value, because when you do installation, then you are not able to achieve such values. So you go with a much stricter value, and over the period of time when you are not doing proper maintenance, then this value does not come. So we generally go with much lesser value to be on a safer side. So this is your design criteria for stray currents. This is for single track. For double track you have to multiply. Now in this case, your rail insulation resistance will become 1 over GRE, and if you do this, it becomes 20 ohm kilometer. Now this is not per kilometer, it is times kilometer. Insulation resistance is always given ohm times kilometer, whereas the resistance of a conductor is given, suppose we take it as 20 ohms per kilometer. So as the length increases, the resistance shall increase, whereas in case of insulation resistance, the resistance will decrease. Why? This is because suppose this is your running rail and it is insulated. So how running rail is insulated? It is generally through the insulation paddings. Now this insulation padding is kept at every 600 mm or 750 mm. So that means there will be some resistance at this point, resistance at this point. So all these resistance will come in parallel. So if you go for suppose 1 kilometer, so there will be a lot of resistance in parallel. So once they are resistance in parallel, then the effective value will decrease, not increase. So that is why the insulation resistance decreases with kilometer. Also, I will give a derivation at the end of this lecture, those who want to enjoy the feel of why insulation resistance decreases with length. Now, The other two criteria provided in clause 5.3 of EN 50 122-2 is the potential shift between the steel in the concrete structure and the earth in the hour of highest traffic shall be lesser than 200 millivolts, plus 200 millivolt. Now in case of higher traffic, once the train is running on this, here they are running rails. So once the trains are running in case of higher headway, in that case there will be more amount of current flowing, so there will be chances of stray current to leak. So there will be more stray current entering, and it will be going from this rebars, it will enter inside this and going, some current will be going longitudinally and some current will be going through this column to the earth and to the nearby structures. So these are your dedicated rebars in the pier structure, and they are connected through these earthing cables. We'll be discussing in detail about these systems in the upcoming lectures, how shear connector has to be connected and all. But just understand here that you take this potential, that means this is your structure, this is your pier, and from this there is an earth terminal taken out, and from this earth terminal you measure using a potential recorder. This value with respect to the reference electrode shall be lesser than 200 millivolts in case of highest traffic. The other one is for the longitudinal voltage drop shall be smaller than this 200 millivolts between the any 2 points. Now this longitudinal voltage drop, if you take a top view of this, so suppose this is your track slab, they are connected with each other, and there is this, the rebars are there inside and they are also connected transverse direction and longitudinal direction. So suppose this is your one section. So if this is your longest section, then the voltage across any 2 points, so this will be the largest. So voltage across these 2 points between any rebar or this shall be lesser than 200 millivolts. These are the two criteria. This, how it is calculated, it is given in Annex C2 of EN 50 122, which we will be discussing how to perform the calculations, but just a reference I am giving you. Now these are the three criteria how the how the stray current system has been designed and how EN 50 122-2 provides for track slab or the reinforced structures. Now we have to discuss about the insulation resistance, why it is inversely proportional to the length. Suppose this is your cable and this is your conductor. Now cable has complete insulation, whereas running rails are only bare conductors which are having insulations at particular intervals. Let us do the calculation or the derivation for the cable. So in this case, this is your conductor which is carrying the current. The current is normally flowing in the conductor, but there are some chances that the current leaks out. This is what we try to do when we do the Megger test. The IR test or the HV test, we check the milliamps in HV test. For Megger, we generally check the milliamps, then it calculates the insulation resistance. So as the current leaks through this cable, it is going in radial direction. So once the current is going in radial direction, you see the cross section area keeps on changing. You cannot define a particular value for this resistance. Earlier the cross section was green, now it is blue. Again it will go and up to the black. So keep on. So as you move ahead, the area keeps on changing. So I cannot write down just direct formula, that is R equal to rho L by A. This cannot be written because this A is completely changing. So what we will do here, we will derive this formula. We will take a smaller element. So if we take a smaller element, suppose this is your cable and this is your conductor. So let us suppose at distance x from the center of this conductor, there is a cylinder and then there is a cross section, and at distance dx, that is from here this distance is x plus dx, that means this thickness is only dx. So the cross section area at this point, that is point 1 and point 2 are nearly same. The cross section area for a cylinder like cable is cylindrical. So for a cylinder, the curved surface area is given by 2 pi r that is your radius, times the length. So in this case it will be 2 pi xl, the other will be 2 pi x plus dxl, which is nearly same. So if the area is same, now we can write down this formula. So the current is flowing only in this section, in this dx length. So your resistance will become rho, L here will become dx, by area it will be 2 pi xl. So this can be written as dx upon 2 pi l x. So now if you integrate these from 0 to r, and here it will be going from leakage will start from this part. So let us suppose the radius of the conductor is a and the outer radius is b. So this is a and OR is b, the outer radius. So if you solve, rho upon 2 pi l will come out common because this is constant, and dx by x will become natural log x from b to a. So I can directly write b upon a. So you see the insulation resistance or the leakage resistance here is inversely proportional to length, whereas the actual formula states rho L by A, that means directly proportional to length. That is why we confuse in case of writing insulation resistance for running rails. We generally, in the standard it is mentioned ohm into kilometer, but generally what we do, we write ohm per kilometer. So remember this. This is also helpful if you see the measure. For a longer cable, this measure will decrease the measure value or the IR value. Similarly for HV, higher amount of leakage current will be flowing once the length increases. So this is the reason why it happens, because resistance is inversely proportional to the length. So I hope you enjoyed the lecture, and please subscribe to my channel, and God bless you all.